So I have adapted my slides. In particular, I took into account the talks of Pat and Watson, and also I have changed a little bit let's say the presentation to be, I hope, smoother. And oh, please. Okay. So I recall where you can find the slides, but I'm pretty sure that you already find it. And, so I will speak of several data, and it is possible to recover everything from here. So I think that you have a README file which explains all the formats. So of course everything is compressed because it's very large. So already when it is compressed, it is something close to 4 gigabytes. When you uncompress it, it's very huge. So if you want to download everything, be sure to have a large bandwidth.
Can you download parts of it?
Yeah, of course. Yeah. That's okay. Just as I was mentioning, so yesterday, so it's just to keep the notation. Okay, it's not. I am not going to remind you of what has been explained last week. So it's just for the notation. So you see, I will design by at the gram associated to a vectors, and by extension, I will use a at in order to denote the convex O of a set of gram vectors. And in particular, I will use it for mainly minimal vectors of perfect forms, which will be the vertices of our polytopes. So as we are going to deal with perfect forms in general. So I will denote by perf n the number of non-equivalent perfect forms, and we know, as it was explained by Renaud Coulangeon last week, we know that this number is finite by work of Voronoi. And we know from, so we have a bound below and a bound above. By Basher, we know that it grows at least exponentially, and by von Verden, we have this bound, the number of perfect forms. So really, I mean, maybe we could think that the correct bound is exponential discrete, something like that, with this dimension. Oops. Yeah, wow. Okay. So if we have a perfect form, so sometimes I will denote by, let's say, if we have a perfect form H of rank n, I will denote by mh the number of minimal vectors up to inversible. So it means that you will have to do a choice. So in the case of this, so it is just plus minus 1. And we'll denote by mh the set of those mh minimal vectors. And you have to keep in mind that once you do labeling of the vectors, intrinsically you are doing ordering on the vector. And as we are we are performing computations, and in few minutes we will speak of orientation. So this ordering is very important. And it turns out, in fact, in all the what's so-called Voronoi complex, we have several types of orderings that we use. And it has a direct on the amount of computations that to perform. So in particular, if you do it the wrong way, you could, literally speaking, multiply by 1,000. Okay. So it's not a teeny issue.
Is that heuristics you're talking about?
No, it's not heuristic.
It's a theory.
Yeah, it's yeah. Because in fact, what you are doing when you go through the form, when you build the representative, if you look at it as a complex senses, you will say, okay, you are doing a sorting. Okay, and if you do it the wrong way, you will be in a complexity in O d squared with b number of input. And of course, from computer science, you know that the best sorting is in d log d. And between d log d and d squared, okay, so you have a log between them. And this is, yeah, you can say it's almost a theorem. Okay, so for each form, I will denote sigma h, the convex hull of mh, so meaning in the symmetric space. So, and Paul is also using this notation, so at least we are coherent. So, as it was mentioned by Coulomb last week, here is what we know on the number of perfect forms, at least what is proved. So here this lower bound is very low, so there are way more, unfortunately. So this lower bound was already due to Van Verden. So of course all those results are exact. And here also give you ideas of what is going on in the Hermitian case. So I put few numbers for Eisenstein integer and the Gaussian integers. So in rank 4, you have respectively 2 and 5 classes. And in rank 5, there are 2007 classes. So it is really up to, say, GLN, well, no, to isometries over either the Eisenstein ring or the Gaussian ring. So it is not up to conjugations, okay? We can,
Sorry.
yes.
What do you mean by hermitian perfect form? Does it mean you go symplectic? The symplectic case here?
No, well, I mean, I take the sesquilinear form.
Because it's in
Yes, yeah, yeah. And so, in fact, so yeah, Renaud was very short last week. The same way than in the Euclidean case. And we are computing the rank 5 currently, not necessarily the fastest way, but and we can say that at least we have, let's say, more than 35,000 classes. But nevertheless, here I mean, those numbers does not mean necessarily that computations are going to be difficult. So you will need to be smart in the way that you will deal with it. But the geometry here and here is way easier than here, because what you can say is, okay, if I look at a perfect form for Gaussian or Eisenstein integer of rank 4, but if I look at it over Z, I will be in 8 dimensions. Okay. And you're right. And even worse, E8, which is very difficult to deal with here, has also a representation in terms of Eisenstein and Gaussian integers. But the geometry of E8 in this representation is not at all the one that we have in Euclidean case. So it's way more easier. That's really the point. So I think that here, very likely we could go, if we are smart and we are very careful on the algorithm, we likely could go to rank 6. And then it will start to be very nasty. So, again, so we are working with two space, one which is the ideal, which is a set of positive quadratic forms, and it's quotiented by real positive homothéses, Xn. We would be happy to work with zoo space, but unfortunately for zoo space, we do not have, a nice cellular decomposition. So we need to build something for which we do have a cellular decomposition. So it's why we are building this space by somehow adding cusp. Of course, not wild cusps, a little bit more reasonable. And again, we will quotient it by real homothéses. And so it means that the boundary, which will be exactly the degenerative part, and we will have to deal with this boundary. So topologically, we will work modulo this boundary. And as you can see here, the way that we consider the specific cusp, it could remind you what already Jennifer and Peter explained to you about how the Tits building is built and how the Steinberg modulo appear. So yeah, you can say that maybe it is on purpose. And here, of course, we have the standard action, and in the hermitian case, you replace this by the star. So this is a consequence of Voronoi results. So if you take the set of all the related to class of perfect forms and their intersection, then you get a cellular decomposition of X star, which is invariant under the action of gamma. So it means that you have a gamma cellular complex.
Just so that I understand, that as a topological space, the dimension of Xn star is the same as the dimension of Xn, and the boundary is one of those. Is that?
Yeah, well, you
No, I mean.
Yeah, I mean here, yeah. So
that's because yesterday when I asked
yeah.
why one did retract because of lower dimension. I'm just trying to.
Yeah. Yeah. So here, I mean, you're right to ask the question, because it turns out that we have several dimensions. You have the topological dimension, and you have also the geometric dimension that you use when you compute the rank. And there is a shift by one between the two. And in order to make matter worse, we compute either at the level of the, let's say, the space, but not of the symmetric space, but at the level of the minimal vector. So in general, the action could be computed either at the level of the minimal vector or at the level of the form. It's not exactly the same types of operations. Oh. So, I mean, this property is mainly what will give you the nice property, the topological property, but still saying that we can manipulate easily the cells at the level of the what we are going to call the Voronoi complex. I mean, the point is here is to say that it will be easy to perform the computations. Okay. And so what we will work with cells which are well defined, and in particular the minimal vectors are of a full rank. And this is what is usually called well-bounded cells. And it's, so the main fact is that, Xn is contractible with star, and that the quotient by gamma is compact. For the cellular topology, of course, not for the Euclidean topology. Okay. That's, I mean, this sentence. I mean, you cannot remove this sentence. So, concretely, from the computational view, what you need is you need two things. The first one is, of course, the perfect forms, which will give you codimension 0 cell, and the facets of the sigma h, which give you the codimension 1 cell. And once you have that, you can build full geometry of the complex or the Voronoi space. Of course, I mean, you can build it using each perfect form also. You, of course, I mean, at the end, you no longer get a complex, but nevertheless, you have an interesting information. And then you need to glue together all the information for each perfect form. Again, so if we think point of view, you can perform all those computations in parallel. So let's give you an example. It is not, unfortunately, it does not work like that. But let's say, for instance, here we have more than 10,000. For one moment, that all forms are homogeneous, same amount, and let's say the computer with core, you can just perform the computation parallel. Okay, and then you just need to glue together all the information. It is really realizable at this level. Unfortunately, it is not the case. I will explain why at the end, I hope, this lecture, and if not in the other lecture. But because, I mean, the forms are not at all equivalent in terms of computation. So in particular, here, for instance, E8 is even with a quantum. Okay, that's you don't have to dream about it. And so it means that if you want to deal with E8, you need to create new mathematical ways to deal with it. So it's not just the algorithmic. I mean, you really need to be mathematically smart at this level. So far, we are not. Yes.
Your Xn, do you think of it as if you go one further, I think.
Yes, but yes.
Yeah.
I won't, but oops.
Okay, all cells are in R to the n plus 1, n times n plus 1 over 2. Do you think of that space, or do you think of that one up to
No, yeah, up to homothésis. Sorry, yes, there is a minus one.
Okay.
Yeah.
So when n is 3, are you looking at a three-dimensional complex?
No. Soule, a three-dimensional complex is at the level of Xn. Yeah, it's yeah. Okay, that's a good point. I completely forgot about not of the work, but I completely forgot to put some slides about it. So yeah, excellent point. I'm so sorry. Yeah. Here, of course, when n equals 2, you have nice decomposition. And even in the case of, let's say, number rings, because it's just Bianchi groups. Okay. So you do not need to use this model. And for n equals 3, in the case of SL3Z or SL3Z1/2, you have a model as proposed by Hecke, so it is completely very clever. So again, you do not require the Voronoi model at this level. And what is nice is, as you do not require the Voronoi model, you do not create all the bad cups, because bad cups translate into torsions that you need to deal with. But here you don't, and so it means that you recover the full information on the cohomology, I mean integrally. No perturbation from weird torsions. Yeah, very good point. Unfortunately, even for n equals 4, we are not able to find a similar decomposition to the one of Soule for SL3. It is still an open question, but an hard one. Just let you know. Okay. So strictly speaking, okay. So we on one hand we need to build the geometry, so just the cells, and on the other hand we need to build the differentials. But first we need to define the differentials, and it is not that easy, because in fact, I mean, it is not a simplicial complex. You have many simplicial cells, but fortunately, you have also cells which are really far from being simplicials. Again, in particular, well, you have one obvious is Dn, because from its geometry, it's of course not at all simplicial. But E6, E7, E8 are really the worst. Okay, because those are really objects with a very large number of faces, codimension 1 faces. And so, as it was explained by Graham last week, so I mean, with cellular complex, you deal with orientations of the cells. And here, the nasty is that we two levels of orientations. It's a little bit tricky to deal with it. And the two levels of orientation are coming, I mean, it is a consequence of the action. It's because the differentials that we are going to compute is on the quotient, I mean, x star gamma, not on x star n. And I insist on these points that we are directly computing at the level of the quotient. We are not computing first the space and then construct the quotient. I mean, if you do that, I mean, you are just dead, because the geometry of the space is too huge. So it means that we will have to build two sets of derivatives. One, which is let's say, the regular set of representative, okay, of x star n mod gamma, and again, strictly speaking, it's x star n, the pair xn and the frontier of x star n. And then we need also to to fix an orientation and keep only the cells which are for which the orientation is preserved. So preserved by what? By the stabilizer, of course, in the extension of their own stabilizer. So it means that we have to compute often stabilizers of the cells. We did in the past maybe not in the smartest way, because let's say 15 years ago, memory was still costly, but today not that much costly. I mean, most of our servers have at least 1 terabyte of memory, and so we can keep in memory a huge amount of information. In particular, it is very easy to keep all the stabilizers in memory, and it is, of course, faster to just take the result of the computation of the stabilizer memory than computing again the stabilizer of the cell, which is far, of course. Okay. So, now we have to build this differential. So it's something that we did in early 2000 with Gangel and Soule. As far as we know, I mean, we were the first to give explicitly this differential. And you likely, I mean, you could apply this strategy in order to build other differential which are not at all related to Voronoi, but which could be related to just a polyhedron on which you have a group which act on. And so you will look very carefully at the details. More or less, so we have, in some sense, that we have one, let's say, we are going to combine two incidence numbers. If you have in mind the classical description of a differential for a CW complex. So one orientation will be coming from the stabilizer, and one orientation will be coming from, in some sense, the geometry of the cells in the gram representation, meaning in the symmetric space. So somewhere, in some sense, one will be built using the determinant, more or less, and the other one will be built using the stabilizer. And so it means that we have those two orientations, so the epsilon and eta, and of course, you will have to sum all those incidents on all the cells which are equivalent to the bottom cell, so tau here, for instance. Okay. An incidence number between sigma and tau. Sigma is, let's say, a k-dimensional cell, and the image of sigma by intersecting the codimensional face of your complex, you need to find out all the tau prime which are equivalent to all the incidence numbers relatively with respect to this tau prime. Think about it is very natural. Okay? So of course, I mean, the main principle of the differential is the geometric one. Okay, it's just the intersection of facets with codimension one face of the. So you realize how life is easy when you are dealing with a simplicial complex. Okay, so it means that it just translates in formula what I just said. So you could define an incidence number for the Voronoi complex. And so you combine all those two eta and epsilon with respect to all the tau prime which are equivalent to tau. And of course, I mean, for, let's say, for convention, I mean, if tau is not equivalent to a phase of sigma, you just said that the incidence number is equal to 0. It's already mentioned in the general case. So then you could have a general formula, which is in some sense the same than the one for classical CW complex. It's just saying that the differential is just the sum, the differential of sigma is just the sum of all the incidence number between sigma and tau for tau running through all the representative of sigma n minus 1. Meaning that, if you prefer, so for all the tau which are in the image of the intersection of sigma with a codimension 1 cell coming from the space. Okay. So it means that even, of course, this set is going to be finite, always, but very large, as you will see in a few minutes. But most of this number will be 0. Okay. And so, some way, it analyzes the classical differential that you can recursively in the case of a regular. Okay. So this is well described in standard book of algebraic topology. But never speak of the situation when you have a group action on a regular complex, of course.
In some sense, you're up in the upstairs in the cover, which is
yes.
So you are doing it upstairs. It's just that you're
yes.
bringing everything.
Yeah.
So you
Yeah.
are working in a regular.
Yeah. Yeah. And in fact, our first approach was this one, was to building recursively, sorry, by doing lift to the regular space, but it turns out to be very messy. And in fact, we never write it down completely. It's very, very messy. So in fact, this approach is way easier. But nevertheless, so far, what I'm saying is just a claim, because I'm not saying that this is a differential. I'm just constructing a well-defined map. And the claim is indeed, it is a differential. And in order to show this, we will do it in maybe an astonishing way, maybe, because what we will show is that this map is nothing else than the first differential of the equivariant spectral sequence. And it's way easier to do it like this. So we have this object, so the Voronoi space. which is with all the nice topological feature. So you have the machinery described in the book of Brown on in section 7 on equivalent spectral sequence, and you can just apply it because you, as I said, you have all the nice property, and you end up with E1 page, which is given by a group of the stabilizer of the cells, and with the action, of course, on the cell. And here you have to be very careful, even if it is Z here, but it is Z with a non-trivial action. So we denote it by Z sigma. And the action here is the one given by tau. No, sorry, par eta. Okay. Of course, you need to also to compute it. I mean, sometimes action could be trivial, of course. Okay, and so here in this spectral sequence, you really have two universes in some sense. I mean, you have the case where Q equals 0. Here, mainly you will have abelian groups most of the time. And it means that if I torsion appear, then it will appear at this level. Because as soon that Q is going greater than 1, here you have a finite group with a bounded torsion. So bounded torsion that you can control. Okay, you can control it here. And so it means that if you tensor it with well, of course, with Q, but if you tensor it with Z1 over P with all P with P running through all the potential torsions, then we'll kill all those groups. So, CR class that I explained very briefly yesterday. And so it means that modulo the CR class Sn plus 1, then the spectral sequence degenerate except for Q equals 0. And this is, in fact, the Voronoi complex. And the differentials that I just shown here, sorry, is exactly D1. Oh, that's, whoa. So it is, sorry, it is going to be even worse. Okay. And coming from here, this is working properly. So, yeah, what I wanted to say. So as I said, so modulo, so you will have two torsion or you will have a free abelian group. I mean, you will have Z. If you kill the two torsion, then you have for the zero line, well, zero line or zero vertical, depending on the spectral sequence. So you get those free abelian groups, and so you have the D1 on it, and this corresponds exactly to the Voronoi complex. So I'm sorry to say that sometimes I denote the Voronoi complex by Vor n, and I recommend to use this notation. And sometimes I use it Vn, but it's the same. Okay, so So we can prove this. So it turns out that all those, this global strategy works also with in the Hermitian case, in fact. And it is true for both Euclidean and Hermitian model, and as I can likely extend it to other. One interesting point in this differential and the way that it is built is that as we give a direct, we do not say in the formula that d squared equals 0. So it is a consequence of this result. And this is the difference when you're doing recursively the differential in the third way, because you use this relation in order to build it. So it means that it gives you, again, a non-trivial test in order to check your explicit computations. This is really interesting. I mean, because again, I mean, one problem when you are dealing with explicit computation, so even if you are using only exact algorithm, then you can have, you could have error of the software. As I said, I mean, the compiler could miscompile your code, and even it looks correct. And it's very difficult to detect. But also you could have failure with the hardware. You could have, maybe, for instance, just one piece of RAM, which is bad, and which gives you some random flip bits at some point. Okay, so you need to, let's say, the most ideal setting is to have certified computation, but this is very difficult to achieve in general. So the best thing that you can do is heuristic in order to check your computation, and stronger are the heuristic, and more trustable are the computation. So this is one example. And it's particularly interesting when you have a very large differential, as you will see later. You will see also that at some point we just have zero differential, so of course this is not very helpful. Case. Okay, so in fact, more or less I have already said that. How are we going to compute this? So indeed, I mean, there could be a different strategy for computing it at some point. So as I said, so you start with all the perfect forms and all the codimension of the convex O associated to a perfect form. And then you compute the for it, and it's really the first layer of complexity. Because, I mean, if once you apply gamma and you end up with, let's say, a small number of representatives, of minimal vectors in your orbit, if you prefer, sorry. Then the geometry and the equivariant geometry will be way easier than if you have a very large number of minimal vectors in your, and I mean modulo gamma. Is it clear or not? Yeah. So this is, I mean, it's, the complexity is really coming from it, from this. Yeah. So then we intersect each layer of a codimension face with the codimension 1 face or some layers below. You have to prove something in order to do this. And each time you build your representatives. So of course, I'm not going to try to intersect, let's say, a face which is here with a face which is here. So let's say two faces that you know that they cannot intersect. So of course, you can be smart at this level in order to avoid the computations. So of course, I mean, you can say, yeah, but intersecting phase sounds very complicated. And you're right, from a purely geometric point of view, it is. But here, fortunately, everything is parameterized by the minimal vectors. And we have ordered them. So we represent every cells in binary format. Okay. And so it means that intersecting two cells, it's just intersecting at the binary level two integers. And this is it's one of the fastest operations that you can perform on the computer. Okay. Do you understand that? Is it clear for everyone? Yeah. Yes. So, okay, let's say you are encoding all the face on, let's say, a number with let's say, 64 bits from 0 to 63. Okay? Then you have, let's say, V1, V2 for VMH for a given perfect form. Okay? And for instance, if in a given cell, let's say a given cell tau, you say you have the first minimal vector is not on it, so it is 0. The second is on it, it is 1. The third is on it, 1, 0, 1, blah, 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 blah. Okay? So now you have tau prime, the same. And so what is the intersection of the two cells is just tau intersecting tau prime as numbers, okay, as binary.
The AND operator.
Yes. Yes, it is an AND operation. Okay. And in order to be even smarter, so as I said, so we have several ordering in the format. Some which are given by invariant, like numeric invariant. You can order all the cells with respect to this ordering. So the first thing that you do from a computational point of view is that you sort all your family of cells first. So it's just n log n in terms of running time, even less, and with n the number of representatives. And you can believe me. I mean, we tested the non-smart way, and it's clearly night and day.
When you're programming, what's it programmed in C or in?
Yes.
Oh, yeah.
Yeah, of course, it's. I mean, if you use a script language as GAP or Paris, I mean, I mean, you can do that, but it is not as fast. Okay. So again, I insist that what we compute is directly the quotient. And a main tool, so of course, it is not easy to perform is equivalence of cells. How are you doing that? So in fact, we do. I mean, we actually to each cell quadratic form. Well, in fact, it turns out infinite positive quadratic forms by using what we call the barycenter, because up it is really like an iso barycenter. But Martinet told us that in fact that this is all. I mean, it was used several years ago by Rolf-Bacher in order to have some invariant for some problems that he was dealing. So Martinet called it also the Bacher matrix, but we are still. I mean, this is a little bit more explicit from the geometric point of view. And so as you end up, so two cells associate two definite positive quadratic forms, and then you just need to compute isometries between them. And of course, for the stabilizer, you just need to compute the form in order to have it. So for this, we have the Plesken-Souvigny that we used. Nevertheless, this is, I mean, even if we are in low dimension, this algorithm is still costly because we had to perform such operation, I mean, millions. And so we still need to have some fast in order to distinguish the cells as fast than possible. But I want to emphasize one point. Here, if it works so well, because it turns out that going really to plug one cell on the other cell, what we are just computing is to look if there is from one cell, see if there is a non-empty intersection between the cells. But it turns out for the Voronoi geometry, if a common interior point, then necessarily the cells are equivalent. Oh, sorry. Okay. Yeah, so for instance, in Paris, you can use QF ISOM and QF auto that Bill Alembert in the previous week, and this implementation was available since, I think, Paris 2.7, but now we are 213 something. Practice, what we use is we use in somehow facet norm, which is what is called the relative spectrum. Again, this is something that you can compute because you have all the minimal vectors for the cells. So in some sense, I mean, you evaluate the values of your cells with respect to all the minimal vectors. Then you have two ways to deal with it. So either you just build a large number, you take the L1 norm of all the components of the electron, or you build so in fact pairs of vectors, okay, and then you use a lexicographic order on those pair of numbers. The second option give you finer results. But nevertheless, at the end, whatever you use, it's difficult to be able to distinguish 1% of the facets. In general, you are between 90–95%. Sometimes you are very, very close, that you are at 99%. And or two cells with the same invariant and not equal, clearly because of Plesken-Sauvigny. And so it's why we needed to have an heuristic, which is faster than Plesken-Sauvigny, but unfortunately slower than just the relative spectrum. Okay. And you can mod out every numbers by, let's say you can take the largest prime of less than 32 bits in order to have every numbers within this range. It is far enough for all the computations, by the way. Okay, when you do that and that everything is going well, you end up with the set of representatives for GL5 and GL6. So here you have these two sets. So remember that the sigma n star is the full set of representatives, and the one without the star is the one with the compatible orientation. So it is interesting, but you can see that already it could kill you the size by at least 2 more. And so you see also that, of course, the numbers increase, but it is not, it's still doable. So, of course, what you have to look more closely, it's the numbers, the consecutive numbers. For instance, here, for GL6 or SL6, between, let's say, 14 and 13, okay? So you have the differential which comes from here to here, and here to here. So it means that the matrices of the differential at this level is going to be 1000 by 1000. So 1000 by 1000 is very easy. If I'm in Paris, I can do that very easily and quite fast. But, okay, so if I translate the previous results with the differential computation, you end up with these results. The Voronoi complex. Okay, so what you see is first, I mean, you have very few free components, so it's almost zero. And if you have in mind what I discussed yesterday, and this is the deceptive part, we have no high torsion. Okay. Meaning no torsion which is higher than the generic torsion coming from the finite subgroup. Okay. Oh. But now, the are a little bit worse. Here, look at all those numbers. Okay. Millions by 2 millions. And it means that the matrix of the differential, they have a large size. So 2 millions by 2 millions is not something that you can deal easily nowadays. Fortunately, those matrices are sparse in a naive sense. meaning you have, let's say, 99.8% of 0. But this is not sparse enough. I mean, you still have too many non-zero coefficients. This is the first information. It is ill-conditioned. I mean, the matrices. I mean, the matrices are not sparse in the sense of numerical analysis. Because if you look at the eigenvalues and the eigenvectors, they are not sparse. So you cannot apply methods coming from numerical analysis. For instance, in order to compute the rank. So here, what we want to do, as explained Graham last week, we want to compute Smith's normal form in order to get the homology. But it is more difficult to compute Smith's form than to just compute the rank of the matrix. And computing the rank, so of course we have exact method, and some very smart, but the fastest one in general are the ones which are used for numerical computations. Here we cannot use them. Are bad conditions. And so all those computations, of course. So I forgot to say that, for instance, for n equals 5, I have done a demo for n equals 5 just 1 second. N equals 6 is something we can do during a talk, so it's just a few minutes. But n equals 7 not. And even so at the time when where the computations were performed and there have been lots of checking on it. So from A to Z, it took 2 years of computations, including the and including the computation of Smith's normal form. And most trickier one I've done with colleagues from the Applied Maths lab, in particular Jean-Guillaume Dumas and collaborators. But I mean, there are two facts. It turns out that the large matrices of the differential, so in particular the D19, this one, but all those ones are used for testing for exact linear algebra, for fast linear algebra. So they are part of the landmark. So it's funny. I mean, sometimes you see papers where they are testing the matrix and they just kept order. So you can see GL7 D19 in some paper exact linear algebra. And those computation, yes.
You have 2 hours, isn't it?
Yeah, no. Okay. No, I will stop.
Oh, yeah, okay. Yeah.
And here. Sorry. Yeah, sorry. I just want to point out that, so in fact, here with new work, in particular work of Charles Bouillaguet and collaborators, so they were able to compute at least the rank, but I think it's also the case with Smith's normal form, way faster than it was computed, let's say, 10 years ago. Okay. And when I say 10, I mean there are 1,000 times factor. Okay, so I will continue in